So as you can see from the title of this tutorial, we will be basically simplifying the combinational function, to be more precise, combinational Boolean function. And this simplification will be carried out with the help of Cardinal Map, which in short is called K-map. So why we do simplification? We try to simplify the expression of any Boolean combinational function so that there are fewer number of terms in the expression of that function that will lead to smaller number of gates required to implement the same functionality. So this simplification will basically lead to minimization of the circuit size, number of the components required to implement any combinational function. And fundamentally, the simplification or the reduction of number of terms or number of variables in each of the terms in the function expression is based on the axioms of the Boolean algebra. Since using those axioms in general for a function is very cumbersome, it might take a lot of time. So what has been done? A very systematic process has been developed, which is called Cardinal Map, using which we can almost mechanically, with very little thinking, can reduce the number of variables and the number of terms also. So in general, this is going to be our objective, and we will try to take few examples and try to find out the simplified version of the function. So first, here we have a function. You can see 4 variables A, B, C, D, and this has been given in what is called sum of min terms. So these are the various min terms corresponding to which the function will have value 1, otherwise it will be 0. So our objective is to minimize this function. So here we have 4 variables. So there will be total of 16 possible inputs. So in the Cardinal Map, we will have 16 cells like this, and cells along y-axis, they will be designated using variable A and B. So we know that this 0, 0 basically designates the situation when A is complement and B is complement. For example, for 0, 1, we have A complement and B. For third case, AB and then AB complement. Similarly, X directed cells, they will be designated using the remaining 2 variables, which is C and D. And then what we do, we fill this map for all those cases which are mentioned here as the min terms. So these are the min terms, M0, M2, M4, so on and so forth. So for all these min term, function value is going to be 1. So all those cells which designate those given the min terms, they will be filled with 1. So here, for example, we have cell number 0, cell number 2, 4, 5, so on and so forth, up to 15. So once we fill with 1, we will of course have to try to find out the largest possible group of 1, neighboring 1. And these group either should be group of 2, group of 4, or group of 8. So that when we combine them, some of the variables, they get eliminated. And this elimination happens because when you write the expression for sum of all these min terms, the situation will arise where you will have x plus x bar kind of summation. So we know that from Boolean algebra, x plus x bar is always equal to 1. So that way variable x will get eliminated. So this Cardinal map basically tries to implement x plus x bar is equal to 1. So here you can see that we can form 3 sets. Fortunately, each of the sets will have 4 ones. So one is here in the middle. So here when we combine all these 4, what we find is variable A will get eliminated. What will be left is B from the y-axis, and from x-axis variable x C will get eliminated, and we will have D. So one term in the expression for the function is going to be B into D. Similarly, when we combine cells in 4, 5, 6, 7 cells, then C and D, they all will get eliminated because they are on x-axis and they appear in complement and uncomplemented form. So what will survive is only A bar B. And then all these 4 corner cells, they are also neighbor, because by the definition of neighbor, we mean cells where when we move from one cell to the next cell, only one of the variables undergoes from complement to uncomplement or vice versa. So for example, from this corner, top corner to bottom corner, when we move, A undergoes from complement to uncomplement change. So all these 4 corners, they are also neighbors of each other and they can be combined. So when we combine, what we will get is this B and D. No, B bar and D bar. So these are the 3 terms that we get after simplifying or minimizing. But sometimes it is possible to have multiple solutions depending upon how you combine the various cells containing 1. For example, for this case also, it is possible to have various other pairings or groupings rather. For example, here, instead of grouping the 1 in cell number 4 and 6 with 5 and 7 cell, they can be grouped with cell number 0 and 2. So here we can see that we again have 3 groupings, but one of the groupings is different from the previous case. So in this case, the third term is going to be A bar into D bar here. So this problem has, or this function can be minimized in 2 different ways. For both the ways, there will be 3 terms in the final solution, each term containing 2 variables. So if we are given problem or the function in this form, sum of min terms, then the simplification is easy. We can very easily fill the table. So either if we are giving the function in the complete table form or in the form of sum of min terms, then the next step can be done easily. But however, in some of the scenario, the function can be given in form of the variables itself. For example, here, f is equal to x bar z, w bar x, y bar plus w into x bar y plus x y bar. Now, if we are asked to minimize or simplify this type of function, then we will have to introduce one more step which was not present in the previous example. And that step would be to first find out the representation of this function in the sum of min term form or in the tabular form. So this problem is going to be a little bit lengthier. So try to solve this problem. Okay, so for this type of problem where we have been given the function in the form of variables, So there are two ways in which we can rewrite the function in as sum of main terms. First is, of course, by uh, including the missing variable in each of the terms. Here you can note that there are actually four variables, and the first term has only two variables, x and z. So w and y are missing. Similarly, from the second term, z is missing, and from the remaining last two terms, again z is missing. So we can multiply each of the terms by 1, and 1 can be represented as, say, sum of w and w complement. So in the first term, we can multiply 1 two times, and in the first case, 1 can be represented as w plus w bar, and the second one can be converted as y plus y bar. So now you multiply and expand. Similarly, for the second term, you can multiply it with z plus z bar and then expand. So that way you will have all the variables in each of the terms, and then you can see that which of the terms represent which mean term. So that is one way, and that could be lengthy if you have more number of variables. That technique works fine for up to three variables. But in this case, what we will do, which is the second technique of finding out the mean term representation of given function. For each of the term, we will try to find out that combination of inputs for which this will give 1. So for example, x bar z will give you 1 whenever x is 0. So we have four variables here, w, x, y, and z. First variable is w, last variable is z. So second variable here is x. So whenever x is 0, x bar is going to be 1, and z has to be 1. So once you fix this x bar or x0 and z1, then w and y, they can take four possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Since they are not present in the first term, so whatever value they take, they will have no impact on the overall value of this. So for all these four cases, we can see that the first term is going to give rise to 1. So this way we can list down all the input combination for which any chosen specific term will always be 1. So this now gives us all the possible inputs for which function will be equal to 1. That means these are in fact also the mean terms for which function is going to be 1. So from here now we can write straightway the function in form of mean term. For example, the first input combination is 0, 0, 0, 1. That means 1. And the second input combination is 0, 0, 1, 1, which is 3. And the third is 1, 0, 0, 1, which is 9. So on and so forth, you can write all the mean terms. And once you have written all the mean terms, you just fill the Cardinal map and do the grouping of ones by trying to combine as many ones as possible, but always in the form of 2 raised power n number in any chosen group. So here you can see that this is one of the possible solutions. So there are two groups consisting of 4 ones and one group consisting of only 2 ones, because here this one is left out. So this should be paired, and this is the only neighbor possible, 11th cell. So we can now have only 3 terms, 3 groups. So 3 terms, 2 terms containing only 2 variables because grouping of 4, and the third one is grouping of only 2 ones. So there will be 3 variables. Elimination of only 1 variable is possible. By the way, this representation is called sum of product representation of the function, because here we have terms and each term is basically product of variables. either in complement or uncomplement form. So now here we have a question. Here again we have to simplify, and so we will have to of course simplify and then represent this in the form of sum of product form, and also the same function as product of sum form. So given any function, we know that it can be represented as sum of certain terms, and terms will be in the form of product of variables, or the same function can also be represented as product of various terms, where each of the term will be sum of various variables. So now we want both type of representation for this Boolean function, which you can see that has three variables x, y, z. So the first part we have already done in the previous two questions, that means simplify and representing sum of product form. So this part we are already familiar with. What is going to be new for this problem is finding the product of sum form. But again, that also should be the simplest expression. So simplify these and find out the SOP and POS. Okay, so for simplifying it and for finding out SOP, we of course need to represent this function as a sum of mean terms, a step which we took for the previous problem. So as I mentioned that there are two ways in which this can be done. One is multiplying each of the terms by suitable term, so that every term ultimately has all the variables present. For example, here we have only x and z, y is not there, so we need to bring y also into picture. So we can multiply this first term by 1, and 1 can be represented as sum of y and y complement. So when you expand this, you will have two terms, each will contain all the variables. So this process can be repeated for remaining three variables, three terms of the function, and ultimately we will have sum of products or sum of terms which will have all the variables, and then we designate each of the variables by their mean term number. For example, this is 0, 1, 0, which is 2. So first term is mean term 2, M2. Now the second term is 0, 0, 0, so which is M0, and third is 1, 0, 0, which is 4, so this is M4, and the fourth one you can see again it is 0, 0, 0, so it is repetition, so we will not place it here. So that way we find out representation of the function in the form of mean term. Once we know it as a sum of mean terms, we can take the help of Cardinal Map to find out the simplified version of the expression, which in this case will turn out to be z bar plus x into y. Because here we can have two groups, one group of 4 variables and the second group consisting of only 2 variables. So this is the simplified version of the expression Boolean function, this expression of this Boolean function z bar plus x into y. And here we see that it is basically sum of 2 terms, and terms in general are product of variables. So this is called SOP form, sum of product form. And this way of representing is also called the standard form also. So now we have to convert this into product of sum. So for such simple cases, there is a shortcut. We can exploit the suitable algorithm suitable axiom of Boolean algebra. For example, here we can exploit distribution of sum over product, which is not there in the normal algebra, but it is there in the Boolean algebra. So here summation of z bar can be distributed over x into y, and then in that case we will get z plus x into, sorry, z bar plus x into z bar plus y. But this shortcut can be taken only when the final expression has fewer terms and fewer number of variables, which is this case. But if the number of variables and terms are more, then we cannot take this route to represent the simplified version of any given function as product of sum. So we'll take another example where we will try to see that how to do that. So here we have another function of 4 variables a, b, c, d, and this is given as product of some form, not necessarily in the simplest form. So here again we have to find out the representation of this function in the simplified, in the simplest SOP and in the simplest POS. So try to find out. So since function is already given as product of some form, so it will be easier to first find out POS form, and then we will go to SOP form. So here in product of some form, the function is 0 for the certain inputs. So we focus on those inputs for which function is 0, and then we write the expression for the function. So this function we know that is going to be 0 whenever any of these 4 terms is going to be 0. So for example, if the first term is 0, then function will be 0. So now we try to find out all those input conditions for which the first term is going to be 0. So here we see that we have a plus c plus d bar. That means a should be 0, c should be 0, and d should be 1. That means a 0, c 0, and d, which is the last variable, is 1. Since b is not there in the sum of this first term, so b could be either 0 or 1. So that means there are 2 possible inputs for which the first term is going to be 0. And those inputs are 0, 0, 1, that means 1, and 0, 1, 0, 1. So this is 5. Similarly, for the remaining 3 terms also, we find out those inputs for which these terms, they are going to be 0. So here now we have all the possible inputs for which function will be 0, because their corresponding sum term is going to be 0. Now these are the inputs which are called max term. So max term is sum of all the variables such that it is going to be 0 for any given specific input. So in this case, we will be able to write the function as the product of max terms. For example, here, this is the first max term, this is the 5th max term, this is the 13th, so on and so forth. So the given function as the product of max term will be given by this expression, pi capital M 1, 5, 13, 15, 9, 11, and 10. So the function has been now represented as product of some terms, or the product of max term. So from here we can proceed in 2 ways. Either from here we can find out the function in the form of sum of mean terms, which will be complement of this, or we can proceed from here to the Cardinal map and try to write the function in the simplified POS form. So because we are more familiar with SOP, so let us first try to extract the SOP form for this function. So this is the function in product of max term. So when we convert this into sum of min terms, so we will have all the complementary terms. That means those terms which are not present in the product form, they will be there in the min term form. So in the form of min term, the function becomes sum of min terms 0, 4, 12, 8, 3, 2, 7, 6, 14. So we have been representing the function mostly in this form. So once we know this function, we can fill the Cardinal map corresponding to this, which is given here. And here you can see that we have three groupings, each of 4 variables. That means there will be 3 terms and containing only 2 variables in the sum of product form, right? So this one is sum of product form, and here there is a slight mistake. This is not actually SOP. This is sum of min term. Similarly, this is not POS, rather this is product of max term. So distinction between these two is that in the product of sum form, there will be, of course, product of certain terms, and the terms will contain sum of variables, but the number of variables could be anything. But in POM form, each of the term must contain all the variables. Similarly, in this SOM form, where I will use small m to distinguish that this is min term, not the max term. Similarly, in the SOM form, each of the term which will be product of variables will contain all the 4 variables, for example, for this case. So this representation here is not same as what we have uh, earlier for example, this case. This is SOP form. So these two terms, they do not contain all the 3 variables. But when we write in this form, then all the 4 variables will be present. So there is a sum of min term and sum of product, 2 different representation of the same function. Similarly, uh, product of sum and product of max term. So we should keep in mind the distinction between these 2 shades of product or sum form. So here we have sum of min term. From there we derive the Cardinal map, and when we simplify and write the expression, it is actually SOP form. This cannot be called as the sum of min term. This will be sum of product term. Now we represented function first as sum of max term, and this expression can also be used to simplify the function and get the directly product of sum expression. So what we do, since each of the term in this representation are written for 0 values, so what we do, we fill the Cardinal map now with zeros instead of 1. And all those cells which appear in this product of max term, they are filled with 0. And then we again form the group. So this is now onwards, this is the similarity between previous case. So we again make the group of 0 in 2 numbers, 4 numbers, and 8 numbers, and then try to eliminate the variable. But this time, the axiom which is exploited to eliminate the variable is x into x bar is equal to 0. When we use min terms, we use x plus x bar is equal to 1 to get rid of variables. But this time we are going to use x into x bar is equal to 0 to get rid of variables. So for example, when we have all these four groupings, and in this case, all these four variables, two variables, they will get eliminated, A and B. And what we will be left here is C and D. So keep in mind that we write each term as the sum, and sum is written in such a way that sum is going to be 0 for a specific input. So here input is 0 for C, 1 for D. So corresponding term is going to be C plus D bar, because then only we will get 0 for C is equal to 0 and D is equal to 1. So the first term that we will get is C plus D bar. Now from the second group of four zeros which are in these cells, so here we see that when we combine them, what will get eliminated is B, because B is present in both complement and uncomplement form. Similarly, from the x direction, C will get eliminated. And then we will have A here and D here. But keep in mind that we should add them in such a way that when A is 1, D is 1, the sum should be 0. So we add A bar and D bar rather than A and D. Now this bottom corner has 0 cell, which was not grouped with anyone, so it will be grouped with the left side cell, that is the only neighboring cell containing 0. So in this case, we can see that one variable from the x direction, which is D, will get eliminated, and we will have C from x direction, and we will have A and B from the y direction. So A bar, B, and C bar will be used. So their sum will be used. So what we get here is a product of sum form. Keep in mind this will not be called as the product of max term. This is product of sum form because all variables are not present in all the terms. So this is how we can simplify a function and represent it either in SOP or POS form. So starting from the given expression, we can start either from SOP form or from the POS. If it is given in product form, it is better to start with POS and max term form and then go to min term. So now there are certain scenarios where the function need not have well-defined values for each of the inputs. For example, here, suppose we have a function like this, only this much, then it says that for min term 4, 5, 7, 12, 13, 14, function has to be 1, and for other min term, it has to be 0. So this is the meaning of expression of the function if only this much is given. But in many real life scenarios, it is not required, or the situation does not demand that function should always have either 0 or 1 value for every possible inputs. So we will take up one example also where we will see that for certain input sets, function could be either 0 or 1, it does not matter. So for those input conditions, we explicitly say that we don't care what is the value of the function. For example, for min term 1, 9, 11, 15, function can be assigned either value 0 or it could be assigned 1. The real life scenario is not going to get affected. So we take the advantage of these what are called don't care conditions to get even the more simplified version or the expression for the given function. So this is the function which we have to simplify, and in addition to min term, we have also been specified the don't care min terms. So for this case, what we do, we try to fill the Cardinal map with not only min term for which function is 1, but we also fill the min term for function can have either 0 or 1. And that time we write D to say that it could be either 0 or 1. So once we fill the Cardinal map, we again try to form the groupings, but this time we will also include D in the group if it enlarges our group and if it tries to minimize more number of variables. For example, in this given problem, we see that the D in the 15th cell, that means for min term 15, D can be assumed 1, and that will help us make a bigger group for two bigger group with each of containing 4 variables, right? While the min term 1, min term 9, and min term 11, they are of not much use, so they can be left as it is. That means they can be treated as 0. So here we see that one of the don't care inputs has turned out to be helpful in minimizing the number of variables. So now there will be 3 groups, and the expression will have 3 terms, and we can write a function for this in the simplified form. So this is the function in the simplified form, or sum of product form, the first expression. But now if we are asked to write the same function in sum of min term, then keep in mind that the expression is not going to be this one. We started with the sum of min term expression, but we exploited some of the don't care to get a very compact or simplified expression for the function, Boolean function, which is this one. And now if we are asked to write the same function as sum of min term, then what we will have to do, we will have to definitely include all these min terms which were given to us. They anyway had to be 1, but now one of the don't care, this corresponding to M15, it has been treated as 1. So now this don't care, the M15 actually has become a min term. So this M15 will now get added. So the function as sum of min term will now be given by this expression. So once again, if you are asked to write the function after simplification as sum of min term and the scenario contains don't care, then you include all those don't care which were used in the form of for the elimination of the variables. So older min terms plus don't care, which was treated as 1. Now let us look at a real life scenario where we will encounter don't care. So assume that we have a building which has 3 floors, right? And then we have an elevator installed in it. So we have to create a circuit or design a circuit which will control the opening and closing of the door. So what is the condition for the door opening? Of course, the elevator should be aligned with one of the 3 levels. That is the first condition. And not only that, it has to be stationary. Okay. So there are 2 conditions. Door to open, it should not only align with any given level, and it should be stationary. Keep in mind that when an elevator is moving from one floor to some other floor, it might get aligned with some of the floors, but it will not be stationary. That time door should not open. So our circuitry should produce 1 for opening of the door where these 2 conditions are fulfilled. So now we have to find out a combinational circuit which will do this job. So just try to think how many variables will be there and what will be the function table. Once you have written the function table, you can solve this circuit. So there is a ground floor, first floor and second floor. So you have to find out how many variables should be there in the Boolean function which will represent this problem. Once you have find out number of variables, you can find out the function value for all the possible inputs. One of the variables, of course, has to be to decide whether the elevator is in motion or stationary. So there will be one variable corresponding to this state of elevator. And since there are 3 levels in the building, so we have to have 3 variables where each of the variable will decide whether the elevator is aligned with specific level or not. For example, for the first level, we will have a variable which will take either value 0 or 1. 0 means it is not aligned with the first level, and 1 means it is aligned. So there are 3 variables for level, 1 for motion. So there will be actually 4 variables in this circuit that we will design. So elevator circuit will take 4 variables and it will give value 1 whenever elevator is stationary and it is aligned with one of the levels. So using this idea, we will have to fill the function table. And now this circuit is a function of 4 variables and it will take value is equal to 1 when aligned with a level and stationary. And for other cases, we will take don't care. For example, elevator can never align with floor 1 and floor 2. That means ground floor and the first floor. It is impossible. So that means whenever you have f1 is equal to 1, f2 is equal to 1, that time this function output function could be anything because that input is never going to occur in the real life. Similarly, the elevator will never have input f1 is equal to 1, f2 is equal to 1, f3 is equal to 1. It will never be aligned with all the 3 simultaneously. So using this, we can fill the function table in this fashion here. Right. So elevator is never aligned with all the 3 floors, never aligned with 2 of the floors. So for those cases, we have don't care. And here, this 1 represents motion. That means whenever the elevator is moving, at that time, door should not open whenever it aligns with floor 1, floor 2, or floor 3. So this is alignment with floor 3, floor 2, floor 1, and elevator is moving, so that is why 0. For all other cases, output should be don't care. That means these inputs are never going to occur in the real life. However, whenever elevator is stationary and it is aligned with floor 3 or 2 or with 1, door should open. So output should be 1. And when it is stationary and not aligned with any of the floors, then also door should not open. So this first input condition can occur in the real life, but door should be closed. Only for the 3 cases, door should open. The function output should be 1. And for many of the cases, it will be don't care. So this is the output function as function of 4 variable incorporating many don't care. So now we can minimize it and find out the expression for the combinational circuit which will represent this solution to this problem.